Okay, chapter 4, our last chapter. And we've jumped back to chapter 4 because everything we've talked about so far, we've only had a data set consisting of one variable. Okay, they call that univariable data. And in this chapter, they discuss bivariate data. In other words, the data in which two variables are measured on an individual. Okay, so before we can represent bivariate data graphically, we got to decide which variable will be used to predict the value of the other variable. Okay, so the response variable is the variable whose value can be explained by the value of the explanatory or predictor variable. Mostly we call it the explanatory variable. And the first step in identifying the type of relationship that might exist between two quantitative, right? They got to be quantitative variables, is to draw a picture of the data. A scatter diagram is a graph that shows the relationship between two quantitative variables measured on the same individual. Each individual in a data set is represented by a point in the scatter diagram. The explanatory variable is plotted on the horizontal axis, the response variable plotted on the vertical axis. We use the term explanatory variable because it helps to explain variability in the response variable. Okay, so here's an example. The data shown to the right are based on a study for drilling rock. The researchers wanted to determine whether the time it takes to dry drill a distance of 5 feet in rock increases with the depth at which the drilling begins. In other words, how deep is you go before you get to the rock, right? So, depth at which drilling begins is the explanatory variable, x, okay, horizontal axis. The time in minutes to drill 5 feet is the response variable, y, vertical axis. And it asks us to draw a scatter diagram of the data, which is pretty straightforward and simple. We go over here, we notice our x's go from 35 to 190, so they've got a scale from about 50 to 200. Okay, and we go to 8, maybe close to 6. So notice they go 6, 7, and 8. And you just plot a point. Okay, x is 35, y is 5.88. So here they've got one. There's 50, so 35, 5.88. Okay, 50, right, basically at 6. 75, they're up to 6.74. At 95, they're down here to 6.1, etc., etc. And you just put a point for each value. Okay? Now be careful. Don't connect the points when drawing a scatter diagram. Another thing is, it's not always clear which variable is going to be the response variable and which is the explanatory. This one's pretty clear on which one is which, but think about, for example, does high school GPA predict a student's SAT score? Or can the SAT score predict the GPA the student has? So the researcher must determine which variable plays the role of the explanatory based on the questions that he or she wants answered. For example, if the researcher wants to predict SAT scores based on GPA, then the high school GPA is the explanatory variable, and vice versa. Okay, so scatter diagrams show the type of relationship, right? Relation mathematically, that exists between two variables. Our goal in interpreting scatter diagrams is to distinguish scatter diagrams that imply a linear relation. Really, that's our goal. But also, it could be a nonlinear relation for later, or no relation. So here's the various scatter diagrams, or some various scatter diagrams, and the type of relation implied. Notice linear relation is implied, another linear relation, because all your dots sort of form a line, right? Linear. This looks like there's definitely some kind of correlation, some kind of relationship, but it's not linear. They're not making a line. Same thing here, okay? And that's just, they're just kind of spread all over, okay? So notice the difference between the two linear, and that's what we're interested in right now, the linear relationships. We could have linear relationships that basically slope up or slope down. Okay, two variables that are linearly related are positively associated when above average values of one variable are associated with above average values of the other variable, and below average values of one variable are associated with below average values of the other variable. That is, two variables are positively associated if, whenever the value of one increases, the value of the other also increases. In other words, when one goes up, the other goes up. Okay? Two variables that are linearly related are negatively associated when above average values of one variable are associated with below average values of the other variable. That is, two variables are negatively associated if, whenever the value of one variable increases, the value of the other variable decreases. In other words, as one goes up, the other one tends to go down. So let's flip back to our scatter diagram and see if we can tell if it had a linear association or not. And it might be a little hard to tell, right? So I would say, yeah, maybe we've got a positive linear association there. Or we also, it looks like, well, maybe there's no association. It's pretty well kind of all over, particularly if I had one more point right there, I'd definitely say no association. So maybe an association. So it's dangerous to use only a scatter diagram to determine if two variables are linearly related. In addition, we can also manipulate the scale or graphs of univariate data. So that means we can manipulate the scale or graphs of bivariate data, which could result in incorrect conclusions. So therefore, numerical summaries of bivariate data should be used in addition to graphs, right, to describe any relation that may exist between the two variables. That leads us to the linear correlation coefficient, or Pearson product moment correlation coefficient. Yeah, that's a mouthful. So we could just call it Pearson's coefficient or Pearson's R. Okay, and it has nothing to do with our book being, or My Lives Plus being a Pearson product. It's from a guy named Pearson back in the 1800s. Okay, so Pearson's R is a measure of the strength and direction of the linear relation between two quantitative variables. Okay, the Greek letter rho represents the population correlation coefficient, and R represents the sample correlation coefficient, and we're only going to talk about the R, the sample correlation coefficient. So here's the formula, where X bar is the sample mean of the explanatory variable. Okay, S sub X is the sample standard deviation of the explanatory variable. Same thing for Y bar and S sub Y, right? Mean and standard deviation for the response variable. And of course, N is the number of individuals in the sample. Okay, here's properties of the linear correlation coefficient. Number one, the linear correlation coefficient is always between -1 and 1 inclusive. Right, so that's how we would write it mathematically. They're a little bit off on their sentence there. So R is between -1 and 1 inclusive. If R is actually equal +1, then there's a perfect positive linear relation between the two variables. If r equals -1, then a perfect negative linear relation exists between the two variables. Notice positive slope, negative slope, right? To help us remember which one's positive and negative. Okay, the closer r is to 1, the stronger the evidence that you've got a positive association between the two variables, and likewise, the closer it is to -1, the stronger the evidence you've got a negative association. Now, if r is close to 0, then there's little or no evidence of a linear relation, but it does not mean there's no relation. It just means it's not a linear relation, so be careful about that. The linear correlation coefficient is unitless, so the unit of measure for x and y plays no role in the interpretation of r. Okay, the correlation coefficient is not resistant. Remember that. Okay, therefore, an observation that does not follow the overall pattern of the data, in other words, an outlier, could affect the value of the linear correlation coefficient. Could affect it dramatically. Okay, so here that is visually, right? Here's if r equals 1, it's a perfect positive linear relation line. Okay, this is r is equal to 0.9, so it's a strong line. It's, we can see an obvious line there. Here we've got it, it's kind of a moderate. R is about 0.4 and moderately linear, maybe, right? Perfect negative, r equals -1, r equals -0.9. It's obviously, there's a strong negative linear relation, and here r is -0.4, maybe a linear association, maybe. Okay, here's r is really close to 0. Both of these are really close to 0, and I can tell, well, no, I don't see any line in there at all. Doesn't mean there may not be some relation, but it's not linear, right? Okay, now in practice, linear correlation coefficients are found using technology. Woohoo, right? But we're going to do one computation by hand, or they're going to do one computation for us by hand, so that we can gain an appreciation of how the formula measures the strength of linear relations. So here's our data from before, and it says we've already seen the scatter plot, but now it says determine the Pearson's R, the linear correlation coefficient. Okay, so what we would do is we would take our table and extend it by 3 columns. First of all, we need to find the mean and the standard deviation from our x and y data. Okay, now here's the formula for Pearson's R down here. And so we would do each step. We would take our point, subtract the mean, divide by the standard deviation for each one. Take the point, subtract the mean, divide by the standard deviation. Take the point, subtract the mean, divide by the standard deviation. Do that for x and y. Okay, and then we need to multiply those two values. This times this goes right here. This times this would go right here. This times this would go right here. Okay, remember what this means. This means sum them. So then I've got to add all of this up and all of this up, right? Okay, and they've done it for us here. So the sum of these, well, the sum of, not all of this, just the sum of this. This is the product. Add all this up. Forget I said that. I don't know what I was saying. Add all this up, right? And then divide it by n minus 1. Oh, notice Pearson's R is 0.7. So, 0.7, yeah, then we thought there was, a positive linear correlation, so maybe there is. Okay, now let's do that with a calculator. And by the way, The steps for that are in your technology tips from the text. And I already have, just to save time, I already have both of these entered in my list 1 and list 2. So if you need to pause and enter that in your calculator in list 1 and list 2. Now this is the first time we've used list 2. So delete your list 1 and enter in list 2. Right? So once you get that entered in, then you're going to press second Y to bring up the stat plots. Okay. Turn on the first stat plot, which we've used. It's probably already on, but so far we've used it for box plots. Let's choose that very first one, or wherever. I'm on an 83. I assume 84 is the same order, but the one that you can see a scatter plot. In other words, the line is just a bunch of dots on there. Select that. Okay. Make sure that your X is in list 1 and your Y is in list 2. Okay, and then let's go to zoom and choose that 9, which is zoom stat. And notice it drew that same scatter plot that we already had done by hand earlier. And remember, you can click on trace to go up and jump from one point to the next, and it'll give you the 2 values if you need to see that. Okay, now to actually find Pearson's R, the correlation coefficient, you're going to have to go into your catalog, right, and turn on diagnostics. Okay, so you're going to hit second 0, the number 0 button. See, it says catalog right above it. Scroll down until where you see diagnostics on. Hit that, hit it again. And then once you have your diagnostics on, you can go back to stat and over to test and select number, not test, calculate, sorry, and select number 4. Okay, and then L1, so hit second 1 to L1, comma, second 2 to hit L2 to tell it list 1 and list 2. Hit enter, and that bottom one down there is your R, and notice it gives me 0.7728 ... so 0.773. So we could get that from our calculator, which is what we're going to do from now on, by just entering our data values. Okay, remember, the linear correlation coefficient is not resistant. So if we had an outlier, maybe one of these that we performed, we put a bad bit on our drill, it might dramatically affect this R. Okay, so one question is, well, how do we know the correlation between the 2 variables is really strong enough for me to conclude that a linear relation exists, right? Is 0.7 strong enough? Is 0.4 strong enough? Okay, well, we're going to answer that with a simple comparison test. So first of all, determine the absolute value of the correlation coefficient. Ours was 0.77 something. And then you've got a new table in your module for course documents and information. It's, you got your standard normal distribution, your student's t. Now you'll see you've got critical values for correlation coefficients. So in the table, how many, let me go back and see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, we had 12 data points. So I'm going to go over to your N is 12 right here, and the critical value. Now they have determined this critical value based on the 5% level of significance, right? 0.05. So, but they've already calculated that for us. It's 0.576. And if the absolute value of our correlation coefficient is greater than this critical value on the table, then we're going to say that a linear relationship does exist. If it was less than that, we'd say no linear relation exists. So notice for this one, if we'd have gotten R to be 0.4, that wouldn't have been strong enough. Whereas on the little charts they showed us, they said, yeah, there is one at 0.4, a moderate one. Okay, so it depends on a couple of things. Okay? Okay, recall. In chapter 1, we stated there's two types of studies. We had observational studies and designed experiments. So the data that we were just looking at was from the result of an experiment, right? It said, they wanted to know this, so they went out and gathered their data. So therefore, since we said, yes, the correlation coefficient and the graph indicated that there's a positive association, we could claim a correlation with a cause, right? But if the data in a study are observational, we cannot conclude the two correlated variables have a causal relationship. For example, look at this. According to data obtained from the Statistical Abstract of the United States, the correlation between the percentage of the female population with a bachelor's degree and the percentage of births to unmarried mothers since 1990 is 0.94. Look how strong that looks. Does this mean that a higher percentage of females with bachelor's degrees causes a higher percentage of births to unmarried mothers? Well, we ought to be able to think about that logically and say certainly not. The correlation exists only because both percentages have been increasing since 1990. It is this relation that causes the high correlation. In general, time series data, right, which is data you collect over time, may have high correlations because each variable is moving in a specific direction over time. Right? They're either both going up or both going down, or one's up and the other's down over time. So when data are observational, we cannot claim a causal relation exists between the two variables. We can only claim causality when the data are collected through a designed experiment. Okay. Another way that two variables can be related, even though there's not a causal relation, is through a lurking variable. Remember that term from weeks ago? A lurking variable is related to both the explanatory and response variable. For example, ice cream sales and crime rates have a very high correlation. So does this mean that local government should shut down all ice cream shops? No, thank goodness, no. The lurking variable is temperature. As air temperatures rise, both ice cream sales and crime rates rise. Okay? So let's look at this example. Because colas tend to replace healthier beverages, and colas contain caffeine and phosphoric acid, researchers and associates wanted to know whether cola consumption is associated with lower bone mineral density in women. The table lists the typical number of cans of cola consumed in a week and the femoral neck bone mineral density for a sample of 15 women. So the data were collected through a prospective cohort study. Right? So if I needed to find my R value, we're going to tell it to you in a minute, but I would enter this, right, in my calculator and let it show me the scatter plot and the Pearson's R. Okay. So the figure shows the scatter diagram of the data. The correlation between number of colas per week and bone mineral density is negative 0.8. The critical value from the table is 0.5. So 0.8 is greater than 0.5. So we can conclude there's a negative linear relation. We can see it on the chart, and we can verify it through that Pearson's R. But can the authors conclude that an increase in the number of colas consumed causes a decrease in bone mineral density? To claim causality, remember, we got to collect the data through a designed experiment. Okay, this was not a designed experiment. It was cohort data. Okay, in prospective cohort studies, data are collected on a group of subjects through questionnaires and surveys over time. Therefore, the data are observational. So the researchers cannot claim that increased cola consumption causes a decrease in bone mineral density. Okay, and they've got a list of some lurking variables in this study that could confound the results. Body mass index, height, smoking, alcohol consumption, calcium intake, physical activity. I can think of a couple more just off the bat. Age, right? Menopause status. Okay, so lurking variables. Now, the authors were careful to say that increased cola consumption is associated with lower bone mineral density because of potential lurking variables, but they never stated that increased cola consumption causes lower bone mineral density. So we got to be careful about that. Okay, let me know if you need anything.